few days ago, I found this article listing different ways to think about the derivative. It started out easy, but by the time it got to number 37, it was very different from the derivative we all know. And that got me thinking. You can think about the same object in fundamentally different ways. In this video, I want to provide a 38th interpretation of sorts, one that links the derivative with topology. It uncovers a result about holes that's so surprising, it may be my favorite piece of math. The essence of the video is as follows. The rules of geometry and calculus fail over weird spaces, and the extent to which they fail measures the number of holes in your space. For geometry, this is called homology. For calculus, it's called cohomology. And the surprising fact is that they measure the same holes. Precisely, this is formulated in Durham's theorem. But if you look it up in any textbook, you'll find that it's quite hairy, so we've got some work to do. Let's get started. Homology answers two questions. How do you define what a hole is? And how do you distinguish between different types of holes? For example, consider a circle and a sphere. They both have a hole, but the hole in the sphere is qualitatively different from the hole in the circle. It seems higher dimensional in some sense. How do we make this precise? Homology does this by looking at the following myth. Given a loop, there's always a region of space that it bounds. This is false in general. If your loop was on a torus, for example, then there's no region on the torus bounding it, because there's a hole. Here's the idea. We can use this as a test to find holes. Now let's be precise. When I say a loop, I mean a k-chain. This is a continuous map from the interval 0, 1 cross itself k times to our shape, which I'm going to call x. Here's the picture. A 1 chain is a curve. A 2 chain is a curvy square. A 3 chain is a curvy cube with the insides filled in. We can now define the boundary of a chain C, denoted del C. This is the boundary of a 1 chain. This is the boundary of a 2 chain. And this is the boundary of a 3 chain. Now let's use this language. A hole is a chain with zero boundary that's not the boundary of anything else. To formulate this in general, we use linear algebra. You have 1 chains, 2 chains, 3 chains, and so on. All of these are vector spaces. The boundary is a linear map that maps 2 chains to 1 chains, 3 chains to 2 chains, and so on. So to find the k-dimensional holes, we just take the vector space of all chains with boundary 0, and we quotient out the chains that are the boundary of something else. This is a vector space denoted hk of x, and it's called the kth homology group of x. Now we define the number of k-dimensional holes to be the dimension of this vector space. That was intense. Let's take stock. There is no new math happening here. We just needed a way to define k-dimensional holes, and we noticed that in lower dimensions this test did the job. So we just defined a k-dimensional hole to be anything that's detected by this test. This modern formulation is due to the genius of Emmy Noether, one of my personal heroes. Now, let's use another, more unexpected tool to count holes, the derivative. Cohomology detects holes in a space by studying functions defined on that space. It looks at when the following myth fails. If a function has derivative 0, it's constant. That's false. Let's define a function on r take away 0. It'll be one number for all negative inputs, and another number for all positive inputs. This function is differentiable everywhere and has derivative 0. But it's not constant. The reason this happened was because there was a hole at 0. Just like before, we can use this as a test to find holes. For higher dimensional holes, there's another myth we have to debunk, one that those of you who study vector calculus may recognize. If a vector field f has 0 curl, it must be the gradient of some function f. Basically, as long as your arrows don't spin around, then when going one way, the vector field is helping you, and the other way, the field is pushing against you. But all of this changes once we curl the domain into a cylinder. Now, you can go to school and back, going downhill both ways. You start here, and you keep going along with the vector field, and eventually you just end up back where you started. And yet, you never spun around. We'll use this as a test to find one-dimensional holes. There's also an analogous test for finding two-dimensional holes. So we have a test for finding two-dimensional holes, one-dimensional holes, and zero-dimensional holes. But these tests look so different. I mean, here we're dealing with functions, and here with vector fields. Here we're dealing with derivatives, here with gradients, here with curl. Is there one unified test to find k-dimensional holes? Miraculously, yes. Instead of dealing with functions and vector fields, we have to look to objects called differential forms. Instead of gradient, divergence, and curl, we'll deal with a gadget called the exterior derivative. The downside with these objects is that they don't have a visual interpretation. Their advantage lies in the fact that they can generalize all these things so that we can talk about them all at once. So what is a differential form? Simply put, it's a formal expression that exists under an integral sign. For example, f of x dx is a differential one form. Its purpose in life is to be integrated over a one chain. An expression that looks like this is a differential two form. Its purpose in life is to be integrated over a two chain. An expression like this is a differential three form. It must be integrated over a three chain. To generalize gradient, divergence, and curl, we need a way to differentiate these forms. The exterior derivative d is defined in terms of these computational rules. The important thing to know is that the derivative of a k form is a k plus 1 form. Unlike the boundary, it goes up a dimension. Here's the point. Let's propose the following test to find k-dimensional holes. If there is a differential k form, omega, with derivative 0, that's not the derivative of some other form, eta, then we've found a k-dimensional hole. In short, a hole is a form with zero derivative that's not the derivative of anything else. Familiar? To be clear, there is no reason to believe this test will actually work. We're just guessing here. But as the hopeful mathematician that you are, you follow the same procedure. Lay out differential one forms, two forms, three forms, and so on in a line. They all form vector spaces. And the exterior derivative maps one forms to two forms to three forms, and so on. Take the space of all differential k forms with derivative 0 and quotient out the k forms that are the derivative of something else. This is denoted h up k of x, the kth cohomology group of x. We might guess that the dimension of this space is the number of k-dimensional holes, but we don't know that. It's true for the homology group, but it's true by definition. How do we possibly prove that this is true? This theorem says the kth homology group and the kth cohomology group are isomorphic, and the isomorphism is given by the integral. Send a k-chain c to the unique k-form omega such that the integral of omega over c is 0. When I first saw this, I didn't know what to make of it. I could sense that it was profound, but it was so abstract that I couldn't really see the point. So we should pause to think about the consequences. First, this shows that the dimension of the cohomology group equals the number of k-dimensional holes in our space. But there's something deeper going on here. You have two worlds, the world of forms and the world of chains. A form is something you integrate, a chain is something you integrate over. A form with derivative 0 that's not the derivative of anything else is a hole. And a chain with boundary 0 that's not the boundary of anything else is also a hole. These worlds are mirror images of each other. The only thing that would be crazier was if, say, taking the derivative and then integrating was the same as taking the boundary and then integrating. And crazily enough, it is. This is called Stokes' theorem on chains, the fundamental theorem of calculus in higher dimensions. So there you have it, the 38th interpretation of the derivative. The derivative is the opposite of the boundary. And if that doesn't blow your mind, I don't know what will.